Section 8.4, and I asked you guys to work on 51 to 76. We'll start with questions there, or from previous homeworks is fine also. Mackenzie, looks like your hand's up. $58? Sure. So 58 asks us to determine whether the following point lies on the line. So stop talking, please, guys. So our point here is 15, negative 20. And our line is in linear combination form. So just thinking about what this really needs, what we need to be able to do to determine if this point is on this line. Basically, I want to see if there's one value of t that can generate this x and this y coordinate, right? So what I'm going to do is I'm going to take the entire x part and set it to my desired x coordinate, and then take the entire y part and set it to the desired y coordinate. And then I'm going to solve for t and see if I can do that with the same t. So since I can do that with the same t, that tells me that yes, this point is on that line. You just gotta, well, it needs to be the same t that I can use to get that point. But all you're doing is checking to see if, is there a t that I can use to get that point? So I just take the x parts and set it equal to the x coordinate, and take the y parts and set it to the y coordinate, solve for t, see if I get the same t. It's the same idea as what we would do in the IB component form. It's just written a little differently, but it's the same idea. Does that feel okay?
Yeah.
Again, more often than not on these problems, like what you're actually doing is not super complicated.
Yeah.
It's just like understanding, like, okay, what do I have here and what can I do with this? That's because it's all, these are just like, it's new forms, it's a new like mathematical object, like the operations still going on are still kind of like a little fuzzy, and it just, it just takes some time. Who's next? Mackenzie.
And then can you also do number
So it just wants the vector line equation that intersects the points. Well, okay, not a big deal. I'll start by calculating a slope. And so I can turn that slope into a direction vector. Now the slope 0, I'm going to think as 0 over 1. So the direction vector I'm going to have is 1, 0. Cool with that, Mackenzie? Okay. My R vector, my point vector, I can use either of these 2 points, or I could find a third point that lay on that line. But like, why would you make it that complicated when you just pick one of the 2 points? Oops, R naught. So I should write that as a point vector. So a point vector plus direction vector times t, and I'm all done. Is this the only answer? No, right? Remember, whenever we write a vector line equation, there's infinitely many vector line equations that represent the same line. Our job is just to find a vector line equation, not all of them. So this may not match what your friend across, the aisle has, but it still could be right. You guys could both have correct answers. Had you picked the other point, you would have gotten a different answer. Had you made your slope instead of 0 over 1, if you made 0 over 5, you'd have a different answer, or 0 over negative 10, you'd end up with different answers. It's still describing the same line. Does that feel okay?
Yeah, thank you.
Yeah, no problem. Again, when we actually came down to doing it, really not a lot to this, right? Just understanding what it is you're doing.
Yeah.
And how you get the pieces you have to remember the form and then how you get the pieces, but getting the pieces isn't hard. The form's not complicated. It's just, getting used to it, right? Just getting used to it. Anyone else? Jackson.
Can you do a projection story problem? I don't have the homework up, but
Okay.
around once.
Yeah, I know what you're talking of. Does anybody else have one of those that they are also interested in? Maybe we can double dip here. 48 you liked? Sure. We can do 48. I'm just pulling up the Word file for the problem set right now so I can steal the problem without having to I guess I could just read it and then write down what we needed. I'll just do that. It's fine. All right, so it says a crate of negligible weight. Right away, that tells me that there's no gravity involved, right? So there's no gravity vector. Is being pulled up a ramp at an angle of elevation of 48 degrees with a force of 150 pounds. Says the ramp, nope, I read the wrong problem. Sorry, it's 105 pounds at 53 degrees. Started reading 49 there for a second. Oops-a-daisy. This is why I should have copied and pasted instead of giving up on that. And then it says the ramp is 15 feet long and 8 feet tall. So we had talked about that just allows us to go straight to component form for the ramp. Okay. I'm going to need the component form for my P. So magnitude times cosine of direction, and then magnitude times sine of direction. I guess let's just get the number there. Got to do it at some point. Might as well be now. So I have 6319 and then 8386. I've already forgot it. 5319, 6319. And then 8386. So what we need then is the magnitude of the projection of P onto R. So that's going to be the dot product of P and R divided by the magnitude of R squared times R. Maybe I should put a parenthesis there. So P dot R is going to be 6319 times 15 plus 8386 times 8. R squared is just, or magnitude of R squared is just going to be 15 squared plus 18 squared. And then we're going to still have to multiply that by r and then take the magnitude. So I'm going to call on my calculator here to help me out for a moment. So 6319 times 15 plus 8386 times 8 divided by 15 squared plus 8 squared. So that's 506, and now I have to multiply that number to 15. And then I have to multiply that number to 8. Times 8. So 8402 and 4481. So that's my projection vector. Now I still just need to take the magnitude of that. And then I'm done. What's up? Sure. So 9522. Because it asks for the amount of force being directed up the ramp. So since you care about the force going up the ramp, you're projecting onto the ramp.
Okay.
So the context of the question told me which one I'm projecting onto.
All right.
Does that make sense?
Yeah. So then the ramp would be like the small.
That's the subscript, yeah, on the projection. Exactly right. Do this, right? Which is what I drew there, right, Mackenzie? No problem. Which again, this is, I think, as complicated as things have gotten so far, right? This one, there's actually like kind of a lot of definitions going on all at once. Easy to kind of get turned around and forget like what's scalar multiplication, what's a dot product, like should I be getting a vector back out of this, or a scalar, or like all that jazz, you know? Because we got magnitudes on top of projections, and then when I unravel that, I got a dot product and more magnitudes in there, and this is kind of a lot. Jackson?
Can you zoom in on the equation part? Like the 15 squared plus 8 squared. Why does that not have a 0?
Because the squared, it's magnitude squared. So like,
Oh, okay. Yeah.
I'm just like, sure, there's that, but those two things are just canceling out. So I just save myself the pencil strokes. But you could write them. It's not wrong to do that. Yeah.
That whole part of like the first or second chapter, you guys don't confuse me. That's for finding component form without.
That's to go from magnitude and direction to component form. Mm-hmm. Yep. Which is one of those you'll definitely want to know. No. That's an expectation, since it's basically the same thing we did when we did the navigation problems in first semester. So it's should not feel unfamiliar. We did that same thing to solve those problems. Jackson, are you happy with what I did there?
Yeah.
Yep. So again, this is kind of as bad as it gets to this point. I don't want to say forever because, well, the last sections.
Can you pull up the wording of the problem so I can see like what Mackenzie said about the P out the R, how you would know?
That's not really where I wanted that to appear. Oh my goodness. All right. Really?
What would be an example of like the other way around, if that makes sense?
It wouldn't make sense.
Okay.
Like you couldn't project the ramp onto the pole,
Okay.
right? Like that makes no sense, right? Because the ramp isn't exerting any force.
Yeah,
It's just a direction,
okay.
right?
Yeah.
All that ramp is doing is describing like the direction. So you're pulling and you're not pulling in the exact same direction of the ramp. The question is like, okay, how much are you really helping?
Mm-hmm.
Like of that 105 pounds of pull, how much is actually moving the crate in the direction you're trying to get it to go? Is basically what you're describing here. In this case, you're wasting 10 pounds of force because you're pulling not exactly parallel to the ramp. Now, if you were pulling in the same angle as the ramp, it would be all of your force your projection would just be the same. It just, the amount of force up the ramp would be the amount of force you're pulling. You know what I mean?
Yeah.
So that's all we're really doing here. So on these kinds of questions where you're talking about like figuring out how much are you actually moving in the direction you want it to move, you would never project the direction onto the force.
Okay.
You know what I mean?
Yeah.
I don't know. It's one of those things like when you stop and think about it, it's like, what does that mean? Like the ramp's not doing anything. It's just a stupid ramp. It's just sitting there, right? Like it can't exert any force anywhere, But that's if you're like, it's easy for me to say that because I understand really understand what's going on. You guys are just seeing what's going on. It's like, oh, okay. Well, I guess when you say it that way, yeah, the ramp can't do anything. Like you can only project onto it. You couldn't project the ramp onto something else. Evan.
So are all these like bearing questions? Are they all like with no gravity?
These crate questions? No, I think that the 49 and 50 both involve gravity.
What do you do differently?
And then 45, the only force going on is gravity.
Like, what do you do differently?
Well, it depends. So like 45 and 46, there's still just two vectors. There's the force of gravity and then the hill or whatever. Nothing really is different there. On 49 and 50, you have three vectors. You have a force of gravity, you have a force of the pull, and then you have your ramp or whatever. So on 49 and 50, you want to add the two forces together, the force of gravity and the force of the pull, and then project that new vector onto the ramp is what you would do differently. So you just resolve them both into component form, add the two components, and then do exactly what you do with a one vector problem. It's just like an extra step in the beginning.
Okay. Yeah.
And 49 and 50 are nice because I think they're both unit vector. The ramps are both unit vector problems. So like actually calculating the magnitude of the projection, there's a shortcut for. So it's not even that much. Nico.
The shortcut for the unit vector is you just take the dot product, right?
Yeah. The magnitude of the projection is equal to the absolute value of the dot product. Assuming you have a unit vector that you're projecting onto. In this case, we certainly did not, because it should be easy to look at this and go, well, that ain't no unit vector.
Yeah.
I knew you knew that, but I just wanted to reiterate for anybody that was like halfway listening. Some of us come in and out. It happens. It's the end of the day. Or end-ish of the day. It's after lunch anyways. Food coma started. Okay. Any last calls here? Great. What I'd like to do is I'd like to do sections 5 and 6 here quickly and then take the remainder of the class to allow you guys to work on the homework quiz rather than timing the homework quiz and leaving enough time for making sure I leave enough time to do 5 and 6. Feels like you're potentially getting more time out of that way. So section 8.5, we're going to introduce the three-dimensional coordinate system. So the three-dimensional coordinate system axes look like this. The dashed line, you need to picture one end of it coming out of the board towards you, and the other end like going back into the board, like into Miss Garcia's room. So everybody get ready to get angry. So we name these axes X, Y, and Z. So this is the x-axis, this is the y-axis, this is the z-axis. All students hate this.
Me angry now.
They all want the z-axis to be, to be the dashed line, and x and y and be their usual locations. They're not. So,
Why did you do
I think the original intent was they wanted the XY plane to be sitting on the ground, right? Like this is the plane you're usually working in. And then you have this, the third axis is coming down into it. I don't really know, but that's the convention that we use. So just remember that. For all of these, the positive end for the x-axis is this end, and the negative end is over here. The positive end of the y-axis is there, and negative there. Positive for the z, and negative for the z. So let's say we want to plot the point 3, 2, 5. When we write ordered triple like that, we're just writing them in alphabetical order, so X, Y, Z. In general, anytime you're writing anything that's kind of ordered, we write it in alphabetical order like that. But when I did this, I think the axes were I, J, K. We did this all with linear combination form, so we had the I, J, K axes. Nowadays, I guess we're using X, Y, and Z, which is probably a little bit more natural than I, J, K, but like whatever, they're just names. All right, so let's talk about how we plot a point in three-dimensional space, because that's not trivial. So we'll start by putting some tick marks on our axes. So I'm going to have 3 tick marks in the positive x-axis, 2 tick marks in the positive y-axis, and then 5 tick marks in the positive z-axis. Everybody's okay there? Now, when we graphed things in 2 dimensions, it was really kind of clear how to do that, because you just do x over y up. But now there's like 3 dimensions, but you're doing it on a 2-dimensional sheet of paper, so it's kind of weird. What this basically is going to boil down to is we're going to build a box to do this. So I'm going to start by building the bottom of the box. So one side of my box is going to have length 3. The other side of my box is going to have length 2. And then I'm going to kind of fill in the rest of my box. So this corner here is the corner that I care about, because essentially that's the point 3, 2, 0. I've gone 3 in the x direction, 2 in the y direction, but I haven't gone anywhere up or down on the z-axis. Does that make sense to you guys? Can we see that? So that's the bottom of my box. What I'm going to do now is I'm going to project this now upward into the z direction. Basically, I'm going to start building the sides of my box. So I usually like to start with the back side of my box that's there. And now I'm going to, from this corner, start building the other side. Now I have to estimate that a little bit to be the same height or same length that I drew the other two upper pieces. And then I'll do the same thing from this point. And now I can kind of color in the top of my box. Oops. There we go. Everybody's okay there with the box that I've drawn? So it's this corner here that I'm looking for. That's the point 3, 2, 5. Because essentially what I've done is I plotted 3, 2, 0, and then I lifted that point 5 units in the z direction. Everybody can kind of see that. Essentially what we've done is we drew an xy plane when z is equal to 5 and an xy plane when z is equal to 0. And we've just kind of lifted that plane at 0 up 5 units, and that's how we know we're the point's in the right place. Does that kind of make sense?
So that top right corner in the front square, that top right.
The red point?
The green point.
The green point?
3, 2, 5.
Correct. Yep. Yeah, that's what I drew the arrow for. That's the point we want. Okay, should we try that again? Again, that's not trivial. It definitely feels a little bit strange. So let's just do one more example on that. Oops, that's not what I wanted. Okay, so here we have 2, -3, 0. So again, x, y, z. So I'm going to start by putting 2 tick marks in the positive direction on the x-axis, 3 tick marks in the negative direction on the y-axis, and then 4 tick marks in the positive direction on the z-axis. Feel okay? I'm going to draw the bottom of my box here. Oops. God, this thing is being such a little pain in the you-know-what.
The neck?
Yes. That would be the what. I would have gone with tuchus, but you'll have to ask your grandfather. Because that feels like a grandfather word to me. Or Mr. McCaskey's a grandfather. You could ask him what a tuchus is. I think any grandparent would do, not just your grandparent. I'm going to have to be careful about that joke. Eventually it's going to have to turn into great-grandparent as You guys keep staying the same age while I keep getting older and older and older. By you guys, I don't mean you specifically, but like my students continue to be like 16 years old. And I keep getting older. Okay, so I've done that part. Now I'm going to draw the sides of my box. Basically, I'm lifting the plane that I've just constructed up. So this then is the point that I am interested in. Not too big of a deal, but like a lot different than what we did in 2 dimensions, right? In general, like if you want to use some colors and color code your stuff like I've done here, you're welcome to do that. In fact, I encourage you to do so. If you want to draw the sides of your box with dashed lines or something, I just straight up use pencils, that's all I do. You're welcome to do that as well. You know. All right. So we have points in 3 dimensions. 2 things that probably need to be updated would be our distance formula. For one, in 2 dimensions, remember that our distance formula is just x1 minus x2 squared plus y1 minus y2 squared. In 3 dimensions, well, you just have a third component. But that's it. Works exactly like it would, as we'd hope it would, right? That seems pretty obvious. If we knew the 2D distance formula, we basically have the 3D distance formula. You guys feel good with that? Similarly, the midpoint formula in 2 dimensions was x1 plus x2 divided by 2, y1 plus y2 divided by 2. And then if we have 3 dimensions, we're just going to have a third component, z1 plus z2 divided by 2. That feel okay? And that's it for 8.5. Basically, you just introduce this 3D system. So here we want to, in section 8.6, are just going to update all of the vector notation and operations we had for 2 dimensions into 3 dimensions. So a vector in 3 dimensions, the component form is just like the IB component form the linear combination form again, remember that these vectors I is just the vector 1, 0, 0. J would be the vector 0, 1, 0. And the vector K would be the vector 0, 0, 1. Those guys were called, again, the standard unit vectors. Again, they all have magnitude 1. And they're real important in a linear algebra sense because they form a basis. You don't care what that is, though. It basically means that we can generate any other vector using scalar multiplication and addition and subtraction with just those vectors. If we have the head minus tail rule, if I have let's just so if I have point A that's x1, y1, z1, and point B that's x2, y2, z2, the vector AB then should be in component form head minus tail, head minus tail, head minus tail. Everything so far, is this surprising? No, it's exactly like 2 dimensions. You just have to deal with the z component to it. But everything is the same so far, right? Our magnitude. So for a vector in component form ABC, the magnitude of V would be a squared plus b squared plus c squared, all square rooted. Again, just like 2 dimensions, except you have a third component going on, like whoop-diddy-doo! Yeah, exactly. One thing worth mentioning here, what I'm going to skip is direction. Why am I skipping direction? In 2 dimensions, how do we describe a direction? With an angle measure, right? What the heck does an angle measure mean in 3 dimensions? We don't use angles to describe directions in 3 dimensions. We're going to just be using a direction vector, but we'll see more on that later. That is non-trivial and actually kind of tricky. Our vector operations basically all work the same way. So if I have vector u in component form, vector v in component form, and scalar k, then vector addition still works the same way. U plus v is just u1 plus v1, u2 plus v2, u3 plus v3. Subtraction, same idea, u1 minus v1, u2 minus v2, u3 minus v3. And scalar multiplication, k times u is just ku times u1, k times u2, k times u3. And the dot product, again, same idea. u1 times v1 plus u2 times v2 plus u3 times v3. Nothing different. Oops, I should probably subtract scalar mult, dot product, and all those dot product properties that we gave you in 2 dimensions, those all still hold. They all work still. So really nothing at all is new in 3 dimensions other than this direction piece that I told you we're going to deal with later. So for example, let's say we want, or that we have vector u and vector v. And what we want to do is we want to find 2u plus v, and then graph that vector. Everybody okay? So we follow the order of operations just like we did before. So we'll start with the scalar multiplication. And then I'll convert my linear combination form into component form. And we just add the vectors. We get 3, 2, 5. And then my last thing I need to do then is to just graph this vector. So I'll start by drawing 3 tick marks on the positive end of the x-axis, 2 tick marks on the positive side of the y-axis, and 5 tick marks on the positive side of the z-axis. And let's just start drawing our box. Draw up, draw up. So there's my point, 3, 2, 5, but we want the vector 3, 2, 5, but our component form vector is just going from the origin to that point. So we're just talking about that vector. We get the difference there between the vector and the point. The vector is the line from the origin to the point. I picked kind of a crummy point because it's awful close to the z-axis there, so it's kind of hard to draw it neatly. Oh well. And that's basically it for sections 5 and 6. There's not a lot to it. It's just getting used to using these same vector names and definitions and everything that we had in 2 dimensions in 3 dimensions. But at this point, you guys should be able to do like 77 through 94. That's not going into this week's problem set, but next week's. Remember, for this week, we just need through 50. But next week, we already have 51 through 94 assigned. Yeep! It'll be okay, guys. All right. Homework quiz time. We got like 35 minutes here. That seems like a pretty good chunk of time. Better than we probably would have given you to to do that. You know what I mean? So pencils and calculators. You're welcome. Yeah, power that baby up.
Thank you.
You're welcome. Sure. And in just a moment here, guys, I'm going to write down that projection formula for you guys on the overhead. You'll need it for problem 5. So 1 second, and I'll get that written down. But if you could do me the favor of copying that down, I'm going to kill the projector here in a minute. So that formula there is for the projection of U onto V. Write that down on your paper there, anywhere you want, but you'll use it for number 5. So wherever you want to put it is fine with me, but you'll need that. Oh, I'll probably use that anyways. I guess need is varying levels of true, but